That is, if it is greater than threshold, we can have it as it will fire 1. If it is less than threshold, it will fire -1.
Oh.
Okay, less than threshold, okay, or less than or equal to threshold also we can have it. It will fire -1. So bipolar, that is, it will either it will fire +1 or it will fire -1. Okay. Now it uses delta rule for training to minimize the mean squared error. So we are trying to reduce the error, okay, by using the concept of delta rule between the actual output and the target output. Okay, we are trying to reduce the error. The weights and the bias are adjustable. We are going to adjust the weights and the bias like how we did for perceptron. Okay. Adeline is a network which has only one output unit. It is trained using delta rule. It uses LMS rule. Okay. The learning rule is found to minimize the mean squared error between the activation and the target value. Now, delta rule. What is delta rule? Okay. Window Hoff rule is very similar to perceptron rule. However, the origins are different. The perceptron rule, what we studied, is a Hebbian assumption. It is based on Hebbian assumptions. But delta rule is derived from gradient descent, what we have studied in module 2. Okay, I have already explained you the gradient descent. Okay, it can be generalized to more than one layer. Gradient descent is an optimization algorithm used to find the values of the parameters coefficient of a function f that minimizes the cost function. Gradient descent is the best used when the parameters cannot be calculated analytically. Okay, so what does the gradient descent do? Just to recall, what does the gradient descent do? Okay, so the points are like this. Usually what happens in the gradient descent, what is the problem? If I start with the one step unit, one step, okay, I need to minimize the error. So the error might be somewhere over here. This is zero error, right? This is zero error. So if this is the gradient route what we were discussing, okay, our aim is to minimize the error. So consider this just to make you understand. This is 100 errors. This is 50 errors. This is 40 errors. This is 30 errors. This is 20 errors. This is 10 errors. And this is somewhere at zero error. Okay, this is just to make you understand. This is -10, -20. Okay, this is again, say for example, 20. And 40 errors. 50 errors. 100 errors. Something like this is there. Okay, so if we go for the gradient descent rule, what happens is, if I take one unit of step time and get down, okay, one unit, and then I see I'm rising up. Okay, I have missed the point. So what did I do in gradient descent? I started with a large step, then I took small baby steps, 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 small baby steps. Then I will try to converge at a point where my errors are least. Okay, but in the first unit, okay, then I will be fluctuating between this and this, but I started with one large step and then I reduced with a small baby step. Kindly recall, then I took the derivative, okay, and then we saw about full derivative, partial derivatives, how to take given an equation, then even we solved the problem based on the gradient descent. Yes, you are able to recall, students? Hello?
Yes.
Hello?
Yes, sir.
Okay, so now, in perceptron training rule, what we did in the yesterday's class, okay, the rule stops at the finite number of learning steps. That is, we learned for first pass, we learned for the second pass, and finally we converged at a point in the third phase, and since there were no updation made, okay, the rule stopped. Okay, can you stop execution of an algorithm? Why? After the iteration 3, no changes in weights, so we stopped. But But in perceptron, in this particular delta rule, in this particular rule, Adeline, okay, it continues. That is, we start, right? We are trying to minimize the error. It will start with, just to make you understand, 100 errors, then 90 errors. Okay, then our error will be 0.003, then 0.004. Okay, there we start with, say, for example, if you are getting down, right? So our error will be 0, let's say, for example, 3. Our error is 3. Then our error may be 2.00, then our error may be 1.01, then our error may be 0.0093, then 0092, then 0091, then 0091, then 0095, then 0086, then 0071, then 0083, then 0011, then 0043, then 0051. Here the errors, okay, every iteration, the error will be keeping on reducing. Okay, but it is not going to converge at a point forever. So we are telling it might be forever. Only asymptotically to be the solution. Asymptotically means what? Okay, we will say that after every iteration the error is reduced, so it will converge at a point 0 somewhere down the line. After 100 iterations or 500 iterations or 1000 iterations, we don't know. Here in 3 iterations, we did, right? Here in 3 iterations, we did. Okay, and we came to know that what? Our error has decreased, okay, from 0.02. Okay, after 3 iterations, we stopped. But here, okay, it just keeps going. It just keeps going. Okay. So the architecture of Adeline. Now, please understand, I will tell you here. The main difference between Adeline and perceptron is, what did we do for perceptron, students? Okay, we did, okay, W1 X1 plus W2 X2, okay, plus W3 X3, and we did, right? Yes or no, students? And then we got some value, okay, 3 or 2 or 1, whatever it might be the value. Then we put it to the activation function. The activation function with produced, okay, 1 or 0. Then the particular activation function value was compared with the target output. And then we found out, okay, the error, and then we tried to update the weights based on the error. Yes or no, students? Yes or no? Hello? Yes or no, students? Hello?
Yes, sir.
Yes, sir.
Yes, what about others? Hello, what about others?
Yes, sir.
Yes, sir.
Okay, so that was the perceptron, what we did in the last class. I repeat, what we did in the last class, I repeat. Okay, we did W1 X1 plus W2 X2 plus W3 X3. This is what we did, right? Okay, then the output of this, say for example, if it is 1, we put it in the activation function. We put it in the activation function. Okay, the activation function produced an output either 1 or 0 depending upon the aggregating function of the threshold. Okay, activation function of the threshold. Now, having done that, we compared the activation function output with the target output, and then we calculated the error. But in Adeline, after the aggregation itself, we are going to calculate the error after every phase. We are not going to wait for our activation function to shoot and then calculate the error. No, we are calculating the error just after aggregating it, that's all. And then we are trying to see what is the error with the target output. Is it clear? That's the major difference, students. That's the major difference. Can you see? That's the major difference. Adeline and perceptron. Here we aggregate it, we put it to the activation function. Activation function produced an output. Okay, and based on the output, we calculated the error. But here, what are we doing? Every single step we are going to trying to change the weights. That's all. Every single step we will try to update the weights. Okay, we are not going to let it through the aggregating function. If we want, we can let it, okay, and we can reduce the output, that's okay, fine. But what we will do is, we are going to calculate the weight. This is the target weight, the classified weight. I told you, in the decision tree, whether the student will play tennis or no, the final one, yes or no. So that predicted value is calculated. with the aggregated value, then we will try to calculate the error. And then we will use that particular error to calculate, update the weights. Okay, so that's the architecture. So we are going to use the concept of this one, then we are going to add a bias to it. Okay, then we are going to compare with the target output. Okay, then we are calculating the bias. Okay, sorry, we are calculating the error over here, and then we are going to do the weight adjustment. Okay, then we are going to do the weight adjustment. Okay, so Adeline and Perceptron takes the binary responses, but Adeline takes the continuous responses. Okay, so now what are the common properties? They both are classifier. They both have linear decision boundaries, as I told you, right? Both are iterative. Okay, sample by sample, Perceptron naturally, but Adeline is stochastic gradient descent. I will tell you. Both uses a threshold function to calculate. Okay, both uses iterative. This is also iterative. This is also iterative. Can you see? First one, first two, first three, then we stopped. But here also it is iterative only, but here we will not stop. But we will stop at some time telling that, okay, from now on, it is going to be this pattern. Okay, so this formula I will explain you with the help of the problems. So last, like how we did last class. Okay, but there is a small difference over here. Okay, here we will be using the final output, not the equation function output. I will tell you, and then we will be calculating the error also. Okay, so now what did we do, students? Okay, just to, so since we are the gradient descent, so since we are actually talking about the gradient descent LMS algorithm, I'm going to tell you because this particular outline runs on LMS algorithm. Okay, so we know that delta W n is directly proportional to dou E So we have been seeing, okay, the last time I'm just explaining you the same thing last time what we did in gradient descent. So E of W is a cost function. Kindly recall. Okay, you can just go to the gradient descent video and see. Okay, where EW is a cost function. So E of vector W is given by half E squared. Okay, so we also know that E equal to, it is the target, right, minus of X transpose into weight. So what is this X into weight? What is this X transpose into weight? So why do we go for what is X? This is X1, X2, X3 till Xn. What is this W? Weights, right? W1, W2, W3 till Wn. If I want to multiply this matrix, how will I do, students? So 1 should be in the transfer form, right? X1, X2, X3, and it goes on into W1, W2, W3, into W1, W2 till Wn. So can you see? I'm taking transpose. So X transpose into W. X transpose into W. Okay, D minus of X transpose into W. Okay, so now this, if I do this, okay, so half E squared. So we know that E is given by this one. You know that E is given by this one. So now if I take a derivative of this, dou E by dou W, what will I get? So I will get minus x, right? Constant will go off. It is minus x. Minus x. This is what I'll get. Okay. So now if I take a dou E of W vector by dou E vector, I get E into dou E by dou W. Okay, can you see? So 2 will get cancelled, so I'll get E. Now with respect to E, if I do a derivative, I get this one. So now what is this one? Minus E. That is, this can be written as x, right? Minus x. So I get E power x. Okay, E power x whole vector. So to calculate the approximate gradient descent, we need to calculate the E vector, right? So which has what? E1, E2, E3 till En. So E vector. So E1, E2 till En. So how do I write that? Dou E by W vector by dou W vector equal to E into dou E by dou W vector equal to minus Ex. This is what we have written, right? So minus Ex. So we are using the cap to denote the gradient approximate. Okay, so the cap to denote the gradient approximate. So I can write this as dou E W by dou vector equal to minus of Ex. Okay. So now what is the weight adjustment rule? So weight adjustment rule is, so I have told you, right, the same thing only. I'm writing it in a different variety of way, like how we did in last class. So Wi new equal to Wi old equal to, kindly recall last class. Okay. Now what is Wn? Approximately is given as directly proportional to dou E by dou W. Okay. So approximate is the cap. So the learning rate minus of E power of x. So when we multiply, we get the alpha into E of x. This is what, students, we have been studying. Yesterday I told you, no? So alpha. Okay, this is the learning rate, same. Okay, both are same. Both are same. Okay, learning rate alpha into E. E is the what? The difference, right? T minus of whatever you call it as the target output. Okay, the summation into xi. So yesterday we did. So here we are estimating this one. So but in the sophisticated, what happens is we are estimating the gradient. Even the weights computed are also estimated. So this cap indicates they are the estimates. Okay, this cap indicates that they are the estimates. So LMS. Okay, so if you see this particular sophisticated gradient, how it will be means, so something somewhere it will be like this, something like that. So it is called as sophisticated gradient descent. Okay, stochasticated gradient descent also. Okay, so this is what we have been calculating. So this is how I am just telling you. Okay, these formula I have just told you how it came. Okay, so yesterday we calculated, no, alpha into E into T minus of target. That is for the with respect to target. That is with respect to perceptron. But this is with respect to the gradient descent. Okay, this is with respect to gradient descent. This is how the gradient descent works. This is how the gradient descent works. Now I will show you the problem. Okay, with the help of the thing. Okay. So having said that, okay, I have just explained you. Kindly please recall the gradient descent, all these things. It's the same thing, okay, y minus of the thing, whatever I have written it, this is the expanded form of it. Okay, now let's get into the problem, student. Okay. So implementation of OR function using adder line. So we know that, okay, okay, we are working on the bipolar inputs over here. Okay, we work on the bipolar inputs over here. That is, bipolar input means in the place of 0, right, we are going to replace as -1. So the bipolar inputs will have the activation function +1 or -1. Okay, so bipolar inputs will have the +1 or -1. So in the place of 0, we are going to replace as 1. That is, what is the normal OR formula? 0, 0, 0, 1, 1, 0, 1, 1. This is the normal OR formula, right? So 0, 1, 1, and 1. This is normal OR, right? But bipolar OR means, can you see, 0, 0, I am replacing it as -1 and -1. Can you see? -1 and -1. And 0 is also -1, the target output. Okay, then 0, if I'm replacing it as -1, okay, that is -1 into 1. Can you see? -1 into 1. The target I'm putting it as 1. Okay, then 1 into -1, I'm putting it as 1. Okay, and 1 and 1 is 1. 1 and 1 is 1. You're able to understand, students, what is happening here in bipolar inputs? Hello? Hello?
Yes, sir.
Hello? Okay, and we are keeping this as an input, okay, that x naught value as 1. X naught value as 1. Okay, x naught value as 1. Okay, that is this particular value. And you see, this particular value, and we are keeping it as 1. Okay, this particular value, x naught, we are keeping it as 1 always. Or this particular one. Okay. Now this is the x naught value which is coming at as 1. Okay. Now we will calculate the change in rate, learning rate, bias. Okay. Delta is the change in the ith rate, learning rate, bias. Okay. So now, students, so now see here. So 1, x1 is 1, x2 is 1, our target is 1. x1 is 1, our x2 is 1, our target is 1. Our weights are given as W1, W2 and bias is given as 0.1, and alpha for this particular problem is given as 0.1. Okay, so we know that bias plus Wi, okay, so Wi into Xi, whatever it is, so the bias. Okay, so Wi into Xi into Wi. Okay, so now what is the fluctuation? How many inputs? 2 inputs. So 1 and 2. 2 inputs. So 1 to 2. So W1. So bias plus W1 X1. Okay, this X2 W2. So we are calculating the Yin. So what is the bias given? 0.1. Okay. What is X1, students? 1. What is X2, W1? What is W1? 0.1. Okay, X2, 1. What is W2? 0.1. Okay, so by is given as 1, X1 is 1, W1 is given as 0.1, X2 is 0.1. Now calculating it. Can you see? We are calculating it. When you do it, 0.3. It is 0.3. Okay. Or what did we do? For percent, we let this into the activation function. If it shooted 1, if it is less than the threshold, it shooted 0. That was the difference. That we did it in this. We did it in perceptron. Okay. Similar. Here for weight application, and only if the target and the output does not match, updated. We are going to get weights. Can you see here after aggregating? Can you see, students? We have aggregated. We have aggregated. Can you see? We have aggregated. After aggregating, okay, we are going to update the weights by using this particular formula for weight updation. Okay, we are going to use this weight updation formula, calculate the error, and we are going to update the weights. Now, so weight updation is the same one, but the difference is instead of T in the perceptron, we did T minus of output. Okay, here in Adeline, we will be doing T minus of Y in. T minus of Y in. Okay, that's the difference. Okay, yesterday in the perceptron for weight updation, that too when it does not match, when it was not equal, we updated the weights. But here it is T minus of Y in. T minus of Y in. Okay, Y in is given here. Predicted value. Okay, so the concept, the other thing remains the same. Yesterday what we did. So W1 old. What is W1 old? 0.1. Okay, and into delta T1, W1. Okay, what is W1? Alpha. Alpha is given as 0.1. Alpha is given as 0.1. Into target. What is target? What is target? What is target? 1. Minus of Y in. What is Y in? 0.3. Into X1. What is X1? 1. Which gives us 0.07. Which gives us 0.07. So Wi old equal to W1 old plus delta W1. Delta W1. So what did we do? So 0.1. W1 old is 0.1 into 0.07, which is 0.01. This is the formula I have showed you. This is the formula I have showed you with these equations. Delta W1 is the learning rate. Can you see? This is alpha into E. E is given as what I have showed you into Xi and Xi. Are you able to understand, students, how the gradient descent works? Stochasticated gradient descent, LMS square algorithm. Hello, this is the LMS, which will make sure to reduce the errors. This is the formula which does the reduction of the errors. You're getting the hello? Hello, you're able to understand?
Yes, sir.
Hello?
Yes, sir.
I will show you where the LMS algorithm was. This is the LMS algorithm. Okay, this is the reduction in the errors. Okay, the same way we are calculating for W2. W2 old into sigma W2, that is delta W2. So what is W2 old? Is 0.1. Plus what is delta W2? Is alpha into T minus of Yn into X2. Alpha is given as 0.1 into target is given as 1 into 0.3. Yn is we have taken as 0.3. Okay, into X2. What is X2? 1. It's 0.7. So once we add up over here, we get 0.17. Then the bias. The formula to update the bias is, okay, B old. The bias old is 0.1 into delta bias. Here X1 and X2 will not come. It's just the delta bias. Okay, it's just the delta bias. So 0.1 is B1 old plus delta. What is delta B? Alpha into T minus of In. So the same thing. 0.1 into 1 into minus 0.3. So when we do the math, we get 0.7, just plug in the values, I get here. So the new weights, and then we will be calculating the error. So T minus of Yn. T minus of Yn. What is T? What is T? 1, right? The same thing what we have done here. Okay? T, which is 1. Yn, 0.3. Okay? The whole squared. Okay, the whole square, which we get 4.9. So for the first input, we have got W1, W2, W3. Okay, then we calculated the bias, and then we calculated the error. Okay, then we calculated the error. So these are the values. W1, W2, bias, and the error. Is this very clear till now? Please raise your hands, those who have understood. Quickly, in 10 seconds, I want to proceed to the next step. Please, what about others? There are other 20 students here. Please, I request you to please, if you have doubts, ask me, or else I shall proceed. I'm waiting for that threshold 54, at least 90% of the students. Here, what about the other 9 students? Are they available? Are they not available?
Sir,
Yes?
can you please explain the concept of 1 and minus 1 again?
Which one, ma? This one,
Yes, sir. We have used 1 and minus 1.
No, very simple, ma. Very simple. What is OR, ma? In bipolar means always the input will be in the form of 1 or minus 1, ma. Okay, that is the bipolar. Okay, so now you are using OR function. How does usually an OR function looks like? 0, 0, 0, 1, 1, 0, 1, 1. Alright?
Yes,
Yes
sir.
or no, ma?
Yes,
And what
sir.
will be the output? 0, 1, 1, 1, right?
Yes.
Yes or no, ma?
Yes, sir.
Yes. So in the place of 0, I am replacing this as minus 1, ma.
Okay, sir.
Okay, so that is what? 0, 0 means what, ma? Minus 1, right?
Yes.
So minus 1, I have put here, see.
Okay.
And 0 means what? Minus 1, right?
Yes, sir.
So I have put minus 1 here.
Okay, sir.
Okay, so what is this? Minus 1, 1, right?
Yes, sir. Okay.
And 1, right?
Yes, sir.
So minus 1, 1 and 1, right?
Yes, sir.
So 1 and minus 1, right?
Yes.
And 1, right? So 1 and minus 1 and 1, right?
Yes, sir.
1, 1 and 1, right?
Yes.
1, 1 and 1, right?
Yes, sir.
That's all. Any doubts?
No. Thank you, sir.
Okay. So based on that, we are calculating. Because it is bipolar input, we are going for 1 and minus 1. That's all. And the activation function is also ranges from, in the perceptron, it is 1 and 0, right? So here, if it is a greater than threshold, it will shoot as 1, and it was less than or equal to this one, we are keeping it as minus 1, the target value. Okay. Okay. So have you understood this? Have you understood this one? This part have you understood? Okay. Okay, so now we will go to the next input. Now what is the next input? 1, minus 1 and target is 1. Okay, 1, minus 1 and the target is 1 and the new weights is 0.7, 0.17, 0.17, 0.17, 0.17, 0.17 and alpha is 0.1. Now calculate the same process. So yn equal to bias into W1 x1. Can you see? W1 0.17 into 1 into 0.17 into minus 1, okay, into bias 0.17. So when I do the math, I get this. Okay, so this and this will get cancelled, I get this. Okay, now I will update the weights. Weights for W1, W2 and bias. So what is the weight for W1? W1 old equal to delta W1. What is delta W1? Alpha into T minus of Yin into X1. So alpha is given as 0.1. T is what? Target 1. What is Yin calculated as? 0.17 into 1 into 1 x1. What is x1? 1. I calculate. So W1 old. What is W1 old? 0.17 plus 0.083. I get this. Then W2. Same formula. Okay. So what is W2? Old. W2 old is 0.17 into delta W2. What is delta W2? Alpha into T minus of Yin into X2. What is alpha? 0.1. What is T? 1. What is Yin? Calculated as 0.17 into X2. See, into X2 minus 1. When I do the math, I get 0.083 minus. Okay. So when I substitute this minus of 0.8, I get 0.87. Okay, then bias equal to bias old plus delta bias. So alpha into t minus alpha. So 0.7 into 0.83. Can you see? I've calculated. I get this. Now I calculate the error. So error is target 1 minus of 0.17 the whole squared. So I get 0.67. This is the error. Okay, this is the error. Okay, now, so I have calculated W1, W2, bias and error for the input. Now I will go for this one. Minus 1, 1 and the target is 1. 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 Okay. So minus 1, 1 and the target is 1. W1 is given as 0.25. Latest weights. W2 is 0.087. Sorry. This. Correct only, right? Correct. Okay. Sorry, I thought I have done a mistake. Okay, so W2 is given as 0.087 and bias is 0.253 and alpha. So same formula. Okay, 0. Bias into x1 is minus 1 into 2.53. X2 is 1 into 0.87. Okay, when you do the math, I get this one. So W1 old, we have got W1 old into delta W1 alpha into t minus of y in into x1. So alpha is given as this, t is given as 1, y in is given as 0.87 into x1 is given as minus 1. So when I do the math, I get this. When I plug in the values, I get this. The same way for W2 old is 0.87 into delta W2. Delta W2 is alpha into t into x2. So alpha is given as 1.7 into x2. What is x2? 1. So when I get this and plug in the value, I get this. The same way bias is given as 0.53. Delta B is alpha into t into minus 1. I get this. And when I plug in the values, I get this. So I get the value, then I calculate the error. So target is 1 minus of 0.87 the whole squared. I get the error. I have written the values. Is it clear? So then I go for the fourth value. Minus 1 and minus 1. Can you see? Minus 1. Minus 1 and minus 1. So W1 is 1617. W2 is 1783. Bias is 3343. And alpha. Okay. So then when I plug in the values, I get this one. So when I plug in the values, I hope by this time you should be knowing, I get this value. And when I plug in the values, I get this value. The same thing, I'm doing it for the other part. So I get, and the error I get as 1.01. So W1, W2, W3 and the error. Is it clear till here? Is it clear till here, students? Is it clear till here? Hello? Is it clear till here? Everybody?
Yes, sir.
Okay, now look in here. Look here, students. Now I'm going to conclude. Very important. Kindly please listen. So now after plug in the values, now what am I going is, this is for the first iteration. Okay, this is for the first iteration. So I have got the error here. 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 Can you see? So I have got the error for the first iteration. First input, iteration 1, first input. Okay. Then I have got the iteration 1, second input. Then I have got the error here, iteration 1, third input. I have got the error here, iteration 1, fourth input. Okay, I am adding iteration 1, first input error, second input error, third input error, and fourth input error. So what do I get? Can you see? 3.02. 3.02. Total mean squared after the first iteration. Total mean squared after the first iteration. Can you see? See, look here, students. Okay, so I am getting the error as LMS squared, right? Because gradient descent works on the LMS squared, right? Adeline. Okay, so 3.02. This is for the first iteration. This is for the first iteration. Now students, now the same concept again I am repeating. Okay, with the updated weights. What was the latest updated weights? What was the latest updated weights? These were the latest updated weights. 0.26, 0.27, 0.24. 0.26, 0.26, 0.27 and 0.24. Okay, W1, W2, W3. Then I will put it and I will run it. I will get an error. I will put it and I will run it. I will get an error. Again I will put it. Okay, because the weights will be updated here, the weight will be carried forwarded here. Then the weights will be updated here, weight will be carried forwarded here. The weights will be updated here, weight will be carried forwarded here. So this will be my second iteration. Isn't it, students? Isn't it? Hello? Hello?
Yes, sir.
Isn't it? So now when I add the second iteration error, okay, total mean squared after the second iteration error 1.94. Can you see? It is from 3.02. My error has been reduced to 1.94. Error have been reduced to 1.94. Then after the third iteration error, it is 1.55. So my error has been reduced to somewhere around 1.55. Okay. Then after the fourth iteration error, it has been reduced to 1.41. 1.41. Can you see? It is reducing the gradient descent concept. Hello? Hello? Are you able to get it? What is happening here, students? Hello?
Yes.
Okay. So like that, students, the loop will be repeated for n number of times. And so that now see, we are getting a pattern. See, after first iteration, error is reduced. After second iteration, error is reduced. After third iteration, further the error is reduced. After the fourth iteration, the further error. You run the loop, again it will reduce. Again it will reduce. Again it will reduce. It will keep on reducing. So only I am telling you, it's an iterative approach. And it will keep running and running and running. What did I tell you this point? Continuous forever, converging only asymptotically to be the solution. Asymptotically to be the solution. But in perceptron, finite number of learning steps. But here we don't know infinite number of learning steps. Getting the point? What does it mean by this particular line now? Hello?
Yes, sir.
Hello? This is all about Adeline, students. This is all about Adeline. Hello? Are you able to understand? How many of you have understood? Please raise your hands. And you can kindly also refer the gradient descent also. This is sophisticated gradient descent, is otherwise also called as LMS. Okay, very good. Okay, students, 1 second. Okay, students, you people can leave. Thank you.